Hey, physics continues, although that was a disaster. That's better. Physics continues. So this is part 2 of communication. So what we want to look at now is communication channels. If you're going to communicate, you've got to figure out which sort of technology you're going to use. So if you're communicating using wires or using physical means as opposed to just electromagnetic waves like microwaves or X-rays, that sort of thing, then what exactly are you going to use? Well, wires are pretty straightforward. We've been using wires for a long time, but the most typical, the simplest wires to use are just a wire pair. You've got two wires carrying signals in opposite directions. They're cheap, they're simple, they're easy, but you know the problem is they pick up electromagnetic interference really easily, which means they can easily be tapped. Tapped means someone can tap in and listen into what you are saying, and that easily happens. That's what spies do. It's what movies are made of. So you can tap into wire pairs very easily, so they're not so useful. So what's better is coaxial cable. Now, back onto tapping. Crosstalk is another example where you're having a conversation with your friend on the telephone and you're talking, and suddenly you can hear another conversation happening. And if you're not very nice, you just sit and listen into what the other people are talking about. See if you can pick up something really interesting. Probably you won't, and you shouldn't, but it can happen. It's called crosstalk. Now, if you want to avoid crosstalk or the potential for someone to tap in to a phone call, then instead of using wire pairs, you use fancier stuff called coaxial cable, where there's one wire in the form of a sheath, and inside there's another wire which runs through the middle, and the sheath on the outside basically shields the wire in the middle so the signal cannot be interfered with. So very difficult to tap into it, and you don't get much in the way of crosstalk. But what's better again is fibre optics, because fibre optic cable can carry masses of information at really high speed. Not quite light speed, not quite, because fibre optic cable has a refractive index of about 1.5, I think it is, which means a refractive index is a slowing down factor. So instead of travelling at the speed of light, it'll travel at about 2/3 the speed of light, which you think is still pretty quick actually, given that light can go around the world 10 times in 1 second. So light speed's brilliant, just under light speed is still pretty good, but people who say time is money, they say they'd rather have light speed, so they prefer microwave signals rather than fibre optic cable, but I think that's getting a little bit carried away. Anyway, what are the benefits of fibre optic cable over wires? Well, more bandwidth, so more information can be carried. Less attenuation. Attenuation is the degrading of a signal over time. We'll look at that later. Greater security. It's not affected by electrical interference because, well, it's not electricity, it's light signals. Light signals don't get interfered with by electrical interference. Very light. There's no fire hazard, unlike copper wire. You send too much signal through copper wire, suddenly you've got a fire. Fires are bad. And it's cheap, relatively. On the negative side, electrical pulses need to be converted to light or infrared. Now that takes a converter, and that's quite expensive, quite difficult technology. It's also very difficult to join fibres together. You can join wires quite easily, but joining fibre optic cable together is difficult. It's quite tricky. Let's talk about radio waves. Now, radio waves, we've got lower frequency, longer wavelength radio waves. They can actually diffract around the world. They diffract around the earth, or refract. They can actually bend. They don't have to go in a straight line. That's a good thing. And radio waves above 3 kilohertz, they move in straight lines and they actually attenuate significantly, meaning they degrade with over distance, which means they only have a range of about 100 kilometers, which isn't actually that far. It's about from Auckland to Whangarei, something like that. So radio waves do decay with over distance, and that's not a good thing. Sky waves can go up and they can bounce off the ionosphere, which is one of the layers in the atmosphere, back down to Earth and bounce off the Earth and back up to the ionosphere, which is great, but the ionosphere isn't always reliable, so radio waves basically aren't always that flash. So what do we use instead? Satellites and microwave links. Well, satellites, we know, orbit the Earth, fantastic, and there are various different forms of orbit. There's geostationary, where you've got the Earth let's just pretend this is the Earth. Now the Earth is spinning, but if you've got a satellite that rotates, because it's just at the right distance from the centre of the Earth, it will rotate at the same speed that the Earth rotates, same angular speed that the Earth rotates. It actually sits above the same point all the time, which is brilliant if you want to spy on somebody continually and know exactly what they're doing all the time. You just have a satellite up above them going around the Earth every 24 hours, sitting above that same point in space. Very, very useful. That same point on the Earth, very, very useful. There's also geosynchronous orbits, where it might orbit the Earth in 24 hours, but instead of going around the equator like a geostationary satellite, it'll orbit in a different direction, which means it'll still rotate around the Earth in 24 hours, but it'll be covering different positions of the Earth's surface. And then you've got near-Earth orbit satellites, and they are typically used, they orbit the Earth about once every 90 minutes, which means they go a lot faster, but they are also a commonly used satellite. They're a lot lower, they're a lot closer to Earth, which means if you use them for communications, there's less time delay because they're a lot closer. With distant satellites, sure, the signal travels at the speed of light, but it's got a long way to go, and you can lose a reasonable amount of time. You can work it out. We won't do that right now. Anyway, satellites and microwave links. Microwaves move at light speed, but the distance to a satellite can cause delays. Now there's some debate around how safe microwaves actually are, especially in higher frequencies. So let's get back to this topic we talked about before, attenuation. What is attenuation? Attenuation is the decay of a signal, whether it's a signal in a wire, in a fibre optic cable, or as waves in the atmosphere. Radio waves, as they spread out, the area they cover gets bigger and bigger and bigger. So the signal strength is inversely proportional to the square of the distance. So you can see that it'll decay quite a lot over distance, obviously. Now there's a formula for attenuation, and it just happens to be written here. Attenuation, you can use whatever symbol you want, but I'm just saying AT. Attenuation equals 10 times log to the base 10. Don't do log to the base E, otherwise you'll get everything wrong, and then you'll get low marks, and then you'll cry, and we don't want that. We want you to get good marks. So use log, 10 times log to the base 10 of power out divided by power in. So it's a simple ratio. It's a log of a simple ratio between power out and power in. So let's say, for example, the power in to a certain signal is 1090 milliwatts, and the attenuation in the cable is, we happen to know that it's 18 decibels. Now, little trick here, when it's attenuation in a wire or attenuation over a distance, unless you're told otherwise, it's actually negative, because it's attenuation, it's energy loss, power loss over distance. They don't always tell you, but there should be a negative sign there. Sometimes when there's a signal that's being regenerated, it's positive attenuation. So we'll get to that. So our situation is, we get our formula and we say attenuation equals 10 times log to the base 10 power out over power in. Don't forget the brackets. So let's put some numbers in. So we can say negative 18 equals 10 times log to the base 10 of power out, which you don't know, over 1090. Alright, so that's relatively simple to deal with. We can just make this 1.8 and get rid of the 10. Do you like that? Is that a good thing to do? I think it's a really good thing to do. Then we can take inverse logs of both sides, so we get inverse log of negative 1.8, which just happens to be 0.0158. 0.0158 equals inverse log, that gets rid of the log here, power out over 1090. I should have had that in brackets. Really important to keep that in brackets. So your next step is to multiply this number by 1090. Therefore, power out comes to 17.3 milliwatts. It started at 1090, it's now down to 17.3. So that is attenuation in action, and that's how you use this little formula. Now, because attenuation happens, signals get weaker and weaker and weaker until they become so weak that they're not very useful. So because of this, we can have regeneration stations. Regeneration stations which strengthen the power of the wave and strengthen the power of the signal, so the signal can go the distance until the next regeneration station, and then it can be regenerated again. And because we use digital signals, the quality of the signal isn't lost. So for copper phone cables, every 5 kilometres you need to regenerate the signal. For coaxial cable, because it's better quality, it's every 10 kilometres. For microwave links will do 40 kilometres before they need to be regenerated. Fibre optics, they win this one. They can cover 80 kilometres before they need regenerating. So that's positive attenuation. So in questions, often you'll have a situation where there's negative attenuation through a wire, but then there'll be positive attenuation through a regeneration station, and you need to take both into account. Okay, that'll do us.